Okay, so this is going to be, so yeah, let's recall. We have this P-trace formula. So the setting was like this. G was a Lie group, for example, need not be compact. So, and gamma inside G is a co-compact lattice. Then we took the following operator. So let H be equal to L2 of G mod gamma. So imagine we are putting a, R measure, or we choose an R measure on G, and then we can form this space L2 of G mod gamma, this Hilbert space. Then we have this regular representation. So I think our notation was rho going from G to unitary operators on H, which was like this. So rho G acting on phi. Such a thing. So it's going to give me a new function. So this X is a class, the coset here, then this is going to be phi of xg. So for all x belonging to G mod gamma, and for all phi belonging to this Hilbert space H. So this is a unitary representation because the measure is a hard measure. So it's a unitary rep. And then what we did was to linearize this. Linearize rho. So we called it like R. So this R is now a representation of this L1G to all bounded operators on H. But not necessarily unitary, because we are adding all these unitaries and there's no reason for that to be unitary again. And the way it works is that something like RF of some phi acting on some, again, X is going to be equal to, so we just linearize this action with respect to, so you just average this over this density F. So this is like F of G phi of X G dG over G. So this is steps that you always do in representation. And one of the goals is to understand how to decompose this kind of left regular representation, or this one, in terms of unitary dual of G, for example, what kind of things appears here and all these things. So this is very, very standard step in representation theory. Okay, so now what did we do next? So because now G is a Lie group, so assume that this F actually has really like rapid decay, or actually it's a smoothly compact support on G. Okay. So if you have such a thing, then this operator turns out to be, or F is actually is a trace class operator. And basically doing things that we did similar to, as in the Poisson summation formula, you can show that in fact Rf of phi over x is equal to integral over G over H, G mod gamma, there's no H, it's gamma, Kf, or K of X and Y, phi of Y, dy, where this kernel, kernel X and Y turned out to be sum F of X gamma Y, I should say maybe X inverse gamma Y, gamma belonging to gamma. So it's an infinite sum over this. So let me just make sure that, yeah, it's X inverse, yes. And my notation was, this was Kf. So any such function f on the group defines this kernel, and the kernel is given by that. So then the pre-trace formula, as in case of Poisson summation, as in PSF, which is exactly the case where this G is abelian, we compute the trace of this in two ways. So trace can be computed in two ways. So this is like trace of, so this is a trace class operator on this Hilbert space. So trace of Rf on the one hand is integral Kf xx dx over G mod gamma, but also trace Rf is, it's exactly, so then we have to rely on some result that we are not going to prove, it takes time, that this Hilbert space, this representation actually can be decomposed in terms of ellipse. So this is going to be, so our notation was m pi trace of Rf, I guess we can see here, Rf restricted to h pi. So now what is this? So where this summation is over G hat, this G hat is the unitary dual of G. So this is the space of all unitary irreducible representations of G up to natural isomorphism. So this is the set of all unitary. So unitary is important. Irreps of G up to iso. Of course, there's a natural notion of isomorphism between such things, and then this is the unitary dual, and this is an important space. We'll see one example, one interesting example of it today, actually. So, and this is the multiplicity number of times that pi belongs to G hat, number of times that H pi appears inside, and they decompose the representation, and these guys are finite dimensional. Okay, so this is finite dimensional. I mean, so this notation is not very good. Well, I mean, so here is, so you see L2 of G on H. Yeah, that's my notation. Sorry, there's no H. G over gamma is direct sum of, now this is my notation. So this H pi is not the thing that, it's not the Hilbert space that corresponds to pi. Is the component, is the subspace, finite dimensional subspace here that is defined by this representation. So, but pi in general belongs to G hat. Anyhow, so, okay, so this is kind of evident, that's not a problem. And this one, then there was a decomposition of that. So you start, so there are these two sides that are equal, one side, this side. So this is the geometric side, this is the spectral side, right? So this is the geometric side. This is the spectral side of this p-trace formula. But the geometric side, we can just using this sort of summation and the structure of this. So write gamma as disjoint union of its conjugacy classes. So I mean, this notation sometimes is this. And then here we get that, in fact, this guy, trace of Rf is equal to sum over, there was some volume of, say, G delta over gamma delta. And so I use the notation I, but maybe it's better to use O for orbital integrals, or O of, so what notation did I use? I believe I used O of gamma and yeah, O of gamma F gamma is gamma, and I can say yes. So okay, so this is summation over conjugacy classes. Now this gamma is the centralizer it doesn't matter which one to choose of any representative gamma belonging to this class. In gamma and G gamma also is a bigger group. This is a much larger centralizer of same thing in G. So in the case of abelian groups, this is completely simplified and gave us a sum over basically gamma. Because you see, this gamma was, in the case that gamma was a discrete group, if it is abelian, then its conjugate classes are just singletons, elements of the group. And this was one, this was one, and this was just evaluation. This is an evaluation, turned out to be f of gamma in this abelian case, and this was one, and this was a summation. But you see, in a non-abelian case, it's much more complicated. It's of this form. So, and that's so this is equal to that. So before saying anything more about this general case, let's look at one example, which is kind of the first non-abelian example that one should know really. First. So this is the case of Heisenberg group. Okay. So this Heisenberg group, this is like H3 of R, for example. It's the set of all matrices. One, say x, z, 0, 1, y, 0, 0, 1. Such that x, y, z belongs to R. So just upper diagonal matrices, on the diagonal is 1, and it's upper triangular. So obviously this is a Lie group. In fact, under multiplication, you can of course know that inverse of such an element is again such an element. So H3R. So this is called the three-dimensional Heisenberg group. Over R. In fact, just in general, you can define the n-dimensional Heisenberg group over any ring. In general, Hn of any ring, I believe the ring need not even be commutative. You can take, and you can just go like, not 3 by 3, you can look at 4 by 4, 5 by 5, stuff like that. But so it's a very, very general construction, this construction of Heisenberg group, and it's a very important construction. So in this case, we are just looking at this case that we are interested in. So we are not looking at this case right now. Okay, so now this Heisenberg group is, of course, is topologically, this H3 of R, of course, is isomorphic to R3, right? Topologically. Even smoothly, there's a diffeomorphism. Not diffeomorphism. There's a smooth map from here to here. Just this x, y, z are global coordinates on this manifold. So as a manifold, it has a very simple structure R3. Okay. Right. Okay, so what else? Yeah, so there is a lattice here. You can guess. Lattice is exactly the case you take A to be equal to Z integers. So is H3 of Z. So this is inside H3 of R. Okay. So, I mean, of course, this is a discrete lattice. I mean, it's a subgroup, obviously. It's a subgroup. It's discrete, obviously. And it's also co-compact. So this was one of our conditions that we needed, right? We wanted our lattices to be co-compact. That made analysis very simple. I mean, so to speak, those components were finite dimensional. Now, this is not so difficult. I mean, almost clear, but I mean obvious. But prove it. I leave you to prove it. And in fact, so this manifold, this three-dimensional manifold, H3 of R. I mean, divided by H3 of Z. So it's a three-dimensional manifold. So it's a very interesting manifold. I mean, it is compact without boundary. It's three-dimensional, and in fact. Although I don't need it, but in fact, it's a total space of a line bundle over torus. So there exists a line bundle. I mean, line bundle, I mean, yeah, I would say a real line bundle. Yeah. No, I don't want real. I want a circle bundle. Yeah. So it is the total space of a circle bundle over this torus T2. So in other words, we can embed a copy of S1 inside this space with quotient. So let's call this M now, which is fibered over this torus T2. So topologically, this three-dimensional space is almost like this. There is this torus. Over here, there is a circle. Of course, it's locally a product, but globally it's not a product. So this is a total space. So this is an interesting three-dimensional manifold. By the way, this manifold is called Heisenberg manifold. Yeah, this is one of the examples of Heisenberg manifold. So So now, any questions, by the way, or? Okay. Now, so you might wonder why this is called Heisenberg. I mean, this is called Heisenberg group and Heisenberg manifold and this thing because it has nothing to do with Heisenberg, and that's the best reason to call it Heisenberg group. Well, I mean, Heisenberg is not responsible for this. I mean, really, it's so let me just mention. So let's look at Lie algebra of this. Lie algebra of H3R. Let's denote it by H3. You see, this is a three-dimensional Lie algebra. Lie algebra over R with three generators X, Y, Z that satisfy these relations, commutator of X and Y equal to Z, and this element Z is central. Commutator of XZ is equal to 0, commutator of YZ equal to 0. So this is the center of the Lie algebra. So why this is the case? I mean, it's very easy in this case to see. Let's define X to be equal to this element 0, 1, 0, 0, 0, 0, 0, 0, 0. The infinitesimal generator of motion in this direction. Let Y be equal to this element 0, 0, 0, 0, 0, 1, 0, 0, 0. And let Z be this element 0, 0, 1, 0, 0, 0. Yes, 0, 0, 0. Then you can check that this X, Y, Z, of course, X, Y, Z belongs to Lie of H3. You see, this Lie algebra of H3 of R, no matter what it is, because it's a matrix group, I can always realize it as inside 3 by 3 real matrices, right? For any closed subgroup of M3 of R, we can realize this Lie algebra as such. So these three elements are the three generators of this. I mean, the exact Lie algebra are nothing but matrices that are upper. So let me just write it actually. H. So if I call this H is upper triangular. So this is strictly upper triangular. 3 by 3 matrices. R, right? I mean, this is clear from the definition of M3 of R. So, okay, so now, I mean, you can check these three relations. Of course, these three X, Y, Z form a basis for this space. Now, you can check these relations. You can check these relations. Now, this relation should be now. This is that's the reason it's called Heisenberg group. This relation should remind you of Heisenberg's commutation relation in quantum mechanics. That's the reason this was called Heisenberg group and Heisenberg Lie algebra, maybe. So we call Heisenberg commutation relations. Or sometimes it's called canonical commutation relations, so CCR in QM. In that case, it was commutator of this operator X hat and P hat was equal to I H bar identity, right? So it is like this element, we call it X, I mean, in this incarnation, and this element we call Y, and this element we call it Z. So, so this is Heisenberg Lie algebra. Yeah. So this is Heisenberg Lie algebra, which is exactly you can call H3 the Heisenberg Lie algebra. So it's like you haven't fixed the value of Planck's constant. You allow the value of Planck's constant to be an unknown, a variable, then you really do get this. But it has to be central because of this I here. And H is a scalar, so this shows it is central. Okay, now, so the idea of introducing group was that this has no finite dimensional, or in fact, no bounded operator realization. So this is a fact from functional analysis. You can try to prove it yourself, is that there are no bounded operators that satisfy this. No bounded. So yeah, maybe a more elegant way is like this. No bounded operator realization or representation of stuff. I mean, for finite dimensional, you can easily convince yourself that there is no such thing. You can take trace of left-hand side is 0, trace of right-hand side is not 0. So, but then this argument fails in the infinite dimensional case. So you have to produce a new argument. There are different arguments in that direction. This is a theorem. This is correct. Not only operators on Hilbert space, in fact, there is no realization in any Banach algebra even. Even in a Banach algebra. Impossible. And of course, working with unbounded operators is a bit difficult. So this was the idea of now Hermann Weyl. Idea was that to look at these things not on the infinitesimal levels that they are here, but on exponentiated versions of this, integrated versions of this. So you just replace x hat by e to the I x hat, this operator, and y hat, I mean p hat, by e to the, well, p hat is self-adjoint, so we just put p hat. And this one by exponential of it. Then you can show that indeed these relations satisfy the relations for the Heisenberg group, which I did not write. So let me write it in the Heisenberg group. These elements satisfy the following relations. So let me just write it in H3R. Say now now I'm going to introduce very kind of arbitrary notation. So x equal to like so 1 1 yeah, maybe yes, okay, 0 0 1 0 0 0 1 and y. So this is a very bad notation, but let's stick to that now. 0 and then 0 1 1 0 0 1 and then z. So maybe I call it. Yeah, that's okay. This is just for now. It's a bad notation. So 1 0 1 0 1 0 0 0. Then you can show that the group commutators xy is equal to z. But this is the group commutator now. In other words, x, y, x inverse, y inverse is equal to z. So in other words, you get the relation that xy is equal to z, yx. Right. So this is the group incarnation of the relations for Lie algebra. So that's the reason it's called Heisenberg. Okay. So that's generalities now. Any questions? Okay, so now, so this is the group that we are going to work with, and that's the co-compact lattice. Now, one of the things is this. This is an exercise. This is a nice exercise. Is that this exponential map from H3, so maybe I'll just write H3 of R really to H3 of R. So this is just a matrix exponential map, A sends to exponential of A. It's actually a bijection between these two spaces. I mean, is a, smooth, of course, it's a smooth bijection. So the map is 1, 1, onto, it's a smooth, and it also follows that this inverse as a result is a smooth. So this is a nice thing to remember. I mean, of course, you have to realize that in general, so for general Lie groups, X need not be injective or surjective for general Lie groups. So these are very, very special case. X is not injective or surjective for general Lie groups. So this is, you can prove this easily. That's not difficult, but it's a good idea. Okay, so now what we want to see is there are two things you need. First of all, the unitary dual of this. Unitary dual of H3R. So the question is, do we know all unitary irreps of H3R, of this Heisenberg group? The answer is yes, and the answer is provided by a famous theorem called the Stone-von Neumann theorem. So answer is, so this is an important theorem, both for quantum mechanics and mathematics in general. Stone-von Neumann theorem. I mean, Stone really just, I guess, wrote it down, but he didn't give a proof. Proof was given by von Neumann, and it's a kind of delicate, difficult result, in fact. So it just tells you what gives a description of this unitary dual, as I will recall now. Right. So let me now get to this. So what are So what are kind of easiest irreps of this guy? I mean, one thing we have to know is that the center of this guy, so the center of H3R, I mean, this is Z, H3. And yeah, so let's call this H3, just make it simpler. So the center of H3 is, this is, you can check directly that the center is the set of all matrices of this form. It's going to be matrices of the form 1, 0, and then here there is a Z, and then 0, 1, Z, 0, 0, 1. Z belongs to, this is exactly the center. I mean, center means all elements that commute with everything. This is the center. So of course, I mean, as a group, this is isomorphic to R, right? Now, if you divide this guy by the center, you take, I mean, quotient of this by its center, by the center, you can easily see that actually what remains, you're dividing by this, what remains are these two elements. When you write matrix multiplication, you see that the way that in the quotient these elements act, this is exactly like the abelian group R2. So in other words, yeah, I mean, so the map here is like this, one, say x, z, 0, 1, y, 0, 0, 1, mod center is mapped to pair xy. So this is a bijection. It's a group isomorphism. Okay. So that's one thing to remember. And now, what you can do is this. You can here take any character chi, go to U1, and then compose with this projection map to get a character of H3, right? So we get these characters of H3. So maybe I can call this pi. Then, so first of all, what are characters of R2? So characters of R2, exactly the unitary dual of R2, these are again R2. So this character is of this form. So for any A and B belonging to R2, the character chi AB over XY is exponential of 2 pi I pair xy dot with AB, right? So these are like plane waves. So this is like e to the 2 pi I ax plus by, right? And these are all the characters here. Okay, so you compose then chi AB composed with pi is a character of H3. So now you get lots of irreps because this is one-dimensional and they are distinct. So we get a lot of irreps of H3 by this sort of easy thing. Now, conversely, if you have any irrep of H3, so this character, of course, this character, if you restrict it to center, it's trivial, right? It's equal to 1. It's a trivial character. And conversely, you can show that if you have a character that's trivial on the center, then it's coming from here because of this quotient property, right? And conversely, any character of H3 trivial on center is of the above form. Okay, so this was easy in a sense. Maybe to prove this in last step you have to use Schur's lemma, but that's not difficult anyhow. So this is just some generalities. So now, so the question is: are there irreps that here I should not say character. I should say any. Actually, I can be more general. Any irrep of H3 that's trivial on the center. It becomes a multiple of the it becomes exactly equal to identity. Then is of this form. So yeah. Yeah, this more general statement is Schur's lemma, but that's very general anyhow. Okay, so now the question is, what are the other irreps? So are there other irreps of H3R? I mean, unitary irreps. Right? Are there such things? And the answer is yes. And they are, in a way, what you learn in quantum mechanics. These are basically integrated forms of Schrodinger representations. So let me write it now. So Schrodinger representation. Again, that's not the version that Schrodinger thought about it. Schrodinger thought about the infinitesimal version of this. This is actually due to y. So here is a representation. So let's define this pi t. So let me write it. For any t different from 0 in R, let's define this pi t from this Heisenberg group, H3 of R, to unitary operators on L2 of R. As follows. So pi t of some ABC. It's kind of convenient now. I should have introduced this before. It's kind of convenient to write this, matrix element here as just a row vector. Like I just write 1, A, C, 0, 1, B, 0, 0, 1. So this, we just write it like that. So pi t is going to be the following operator. So on X is equal to, so it's a product of three things. There is a phase factor, there is a translation shift operator, and there is a constant phase modification, which is going to correspond to t, which is related to Planck's constant. Okay, so let me now write this, and then I will explain where it comes from. Yes, it's e to the I h bar c. Yes, exponential of I h bar c, exponential of I e x. This is a constant phase. It's like, yeah. And oh, okay, so this is t, sorry. And this is space factor, and then there is times phi of x plus e a. You shift it by this amount. Yeah. So it's a product of three unitaries. Now, I said this is Schrodinger representation in the integrated form that's given by y. I mean, the reason is that, remember, we had this, basically the relation x hat p hat, which was x hat p hat minus p hat x hat equal to I h bar I. I mean, there is a sort of Schrodinger representation of in quantum mechanics for these operators, right? So x hat, unfortunately now this is an unbounded operator that goes from some domain, it doesn't matter, I just write it from some domain, dense domain inside L2 of R to L2 of R. It's just the operator of multiplication. I mean, sends phi to x phi. And this momentum operator he had phi x is just IH bar, IT d phi dx. Again, your domain should contain maybe smooth functions or one times differentiable function whose derivative is also in L2. You have to fix some initial domain and then show that these operators can be extended to self-adjoint operators. So it's a bit delicate working in the unbounded case like this. And of course, the other one is just phasing by multiplying by this phase into the IH bar. So if you exponentiate these three operators, x hat, p hat, and this multiplication by h bar, you're going to get these three operators. Okay. And then the fact that infinitesimally they generate this relation, they have this relation, implies that in the integrated form, these things, this pi t is actually group representation. In other words, it preserves the group structure. So this you can check easily. Of course, that's not, you can just check yourself by hand. I mean, check that pi t of ABC times A prime, B prime, C prime is equal to pi t of ABC times pi t of A prime, B prime, C prime. By the way, of course, I mean, this is nothing but A plus A prime, B plus B prime, but the multiplication on the third factor is a bit more complicated. It's, I believe it's going to be AB prime plus CC prime or something like that. So there is some third factor here which I forgot. You can just write down the third factor, find here by writing it in this form, in matrix form, I'm finding it. Anyhow, this is easy to check in this case. Also, this is easy to check using those definitions. So this is called Schrodinger representation. Now, the question was, well, okay, so Schrodinger wrote one representation of his of this commutation relations like this. What if there is another representation? Who guarantees that there is no other representation? What if there is some other representation? Then you potentially, you are at risk. You may get a totally different kind of quantum mechanics for the same problem. I mean, the spectrum may change and things might change because this is all that's suggested by quantum mechanics. I mean, this L2 of R and representations are rather could be arbitrary. So this was the question of uniqueness of Schrodinger. So this is the uniqueness of Schrodinger representation. So this is the Schrodinger representation that I erased here, part of it over there, but this is. Okay, now this question, as I said, it's kind of, I mean, yeah, people believe that there is a uniqueness, but it's kind of hard because it's unbounded. That's why Weil introduced this integrated form, and people started trying to prove this result for uniqueness of kind of now is equivalent to uniqueness of unitary reps of Heisenberg group H3R after fixing values of Planck's constant. After fixing value of H bar belonging to R first of all, and you want it to be different from 0. You see, if Planck's constant, you fix it to be 0, then you are in case of classical mechanics. You don't want that. But the question is it true that maybe this thing, the Heisenberg group H3, after all, has a unique representation, which is then given by this? And the answer is yes. And that's a Stone-von Neumann theorem. So that's the justification. So the answer is yes. So Stone-von Neumann. So the answer is up to unitary equivalence. There exists a unique unitary rep of H3R such that its restriction to the center is non-trivial, whose restriction to the center of H3R is equal to, is not identity, because identity corresponds to H equal to 0, T equal to 0, is fixed. So that's the result. That's a any questions? Okay. Now, this result, what we did, gives us a.
Sorry, I have a question.
Yes, yes.
So, why since x hat and p hat they are operators on a Hilbert space, so why are they related to H3, a three-dimensional space? Like you said, we look at the exponentiation, but the exponentiation doesn't lie in H3.
No. I mean, what I'm saying is that these relations. I mean, first of all, there are, as I mentioned before, there are no bounded operators on any Hilbert space that satisfy these relations, right?
Mm-hmm.
So these operators are only densely defined, and you can also take it self-adjoint in that case. So now, but these relations imply that e to the x hat and e to the p hat, right, is equal to some constant, e to the maybe IH bar or something, times e to the p hat, e to the x hat. And if you look at it, I mean, okay, so this needs a proof. I mean, you have to use something like Campbell-Baker-Hausdorff formula, something like that. Once you get that, then you can prove something like this. But this relation, yeah, I mean, these operators are just unitary operators on a Hilbert space, because this is, after all, only one representation of that Lie algebra. You see, if you think about the Lie algebra, it's a universal form of this Lie algebra H3. And the same for Lie group H3 is a universal form of this. So every incarnation of that is, do you understand what I mean?
Okay, so it's kind of there is an embedded H3 generated by these things, and we in order to have good quantum mechanics, we should restrict to this embedded subgroup.
Yes.
Okay.
Anytime you want to have quantum mechanics, because you need a Hilbert space, you have to represent this H3 by unitary operators on your Hilbert space. Then, for example, this A would correspond to multiplication by X operator. I mean, it's exponential. C would correspond to Planck's constant multiplication, and this B would be translations, something like that, right? So it's better to think of in terms of representations of Lie groups, Lie algebras as a universal gadget rather than some particular incarnation, some models of it here or there. So that was a good point. Yeah, good question. Yes. So yeah, that's the reason. Any other questions? Okay, now we can actually now it's a good idea to think of the unitary dual of this. How does it look like? Because now it's a good case. So the unitary dual of so it actually, as a topological space, it looks like this. So you have this plane. There's a two-dimensional plane, and there is one line. So points on this line correspond to infinite dimensional representations. You see that the points here, it's a t. It's different from 0, right? Here, t is different from 0. So this 0 is not part of the line, because all the way up to here, you get infinite dimensional representation, but then points on the plane, these are one-dimensional representations, right? So these are characters. So these are KABs, right? So the line and this plane is the whole unitary dual. So you can just say is this. Okay? So that's what Stone-von Neumann theorem does give you. And the goal of kind of representation theory of infinite dimensional, I mean, any representation theory of any groups in general, is to find this picture for other groups. So any group that I give you, you should be able to produce a picture like this to start with. In other words, how can you label unitary irreps of your group in a nice way? There is some topology, and you see that as a manifold, it's not a smooth manifold. It has singularities, and actually it's not a manifold. I mean, here is one-dimensional, and there's this two-dimensional component. So there is some difficulty with this space, but that's okay. So that's the next step. And the second step that we need is to describe the Plancherel measure here, right? Describe the Plancherel measure. Remember, what was Plancherel's formula from Fourier series and Fourier integrals? So I recall that Plancherel formula told you that integral f of x squared dx, right, over r is equal to integral. I mean, this is a really amazing result that this is equal to r hat. I mean, okay, so first of all, we know it's r f hat of k squared dk. So L2 integral, or L2 norm, so this was like L2 norm of f hat is L2 norm of f, right? This is the result, right? In reality, this is not r, this is r hat. But r hat is canonically isomorphic in this case to r. So there is some identification going on here. Instead of integrating over r hat, because f hat is really a function on r hat, as we saw in many cases. So it's this one, right? This is the Plancherel formula, the original Plancherel formula for Fourier integrals. Also, you have a version for Fourier series. This is, I'm sure you have seen, of course, which is, so this is for Fourier integrals. You can have it for Fourier series. And if you have f belonging to, for example, L2 of 0, 1, for periodic function, you have integral f of x squared x from 0 to 1, right, is equal to sum f hat n squared n belonging to z. Right? Again, you can also see this as integration of this guy over g is equal to integral f hat of g squared dg over g hat. Well, in this case, g is a circle, g hat is just z, right? But by duality, we know that this is, so this relation, and so this relation and that relation are special cases of this very general relation, right? But this is unfortunately only in the abelian case, just for the abelian case. And for any abelian G, there is a similar formula. So that's fine, but now here we have our kind of first non-abelian example. What should we do in this case? What should we do in this case? Well, again, you have to, well, we know what G hat is, at least, right? We know what G hat is, and we know so I'll tell you how to think of Fourier transform in a non-abelian case. It needs some thinking. What is the analog of Fourier transform in this case? But then what you have to work out is what is this measure? Oh, this is not G, sorry, this should be chi, because these are characters and this. Okay, so let me now write it down. Plancherel measure formula. So this is a theorem. I mean, it needs a proof, and it's not very easy to prove. But I mean, you can. I mean, in this case, it's not very difficult. Plancherel formula for H3 of R. So what is it? First of all, The measure on this H3 dual is called Plancherel measure, and the support of Plancherel measure is on R. I mean here. I mean this is the space of T's. Okay. I mean over here there's no measure. I mean all these finite dimensional one-dimensional representations carry no measure. They are totally unimportant for us for the Plancherel formula. So this is already interesting, and is given on R by absolute value of T. The dt is Lebesgue measure, right? So what does this result mean? It means that over here you have to choose a different weight function, not one, this absolute value of T, Lebesgue measure in order to. Okay, so that's one thing. Second is that for any f belonging to C infinite C of H3, the operator okay, so now I have to introduce a good notation here. Okay. Right, so the operator, the notation I'm using is pi t of f. Operator pi t of f for any f belonging to, this is already over there. Schwarz is enough, but that's okay. Is trace class. Actually, it's Hilbert-Schmidt. That's important. Better than. It's Hilbert-Schmidt. And the following formula holds. Integral over R cross. R cross is this space here of norm of pi t of f squared absolute value of t. dt is equal to integral over h absolute value of f of h squared dh. So let me explain this. First of all, what is this dh? dh is the Haar measure on this Heisenberg group, which is not difficult to see that. This I don't want to erase. So easy to see that our measure on H3 on this Heisenberg group is given by this. So integral, say f. So because there are global parameters ABC here, f of ABC. So this is like h dh over H3 is equal to integral over R3. This is just Lebesgue measure, f of ABC dA, dB, dC. So that's interesting. I mean, it's easy to see. You just take definition of global. You have to check that this is translation invariant on the left multiplication and right multiplication. This group is actually unimodular. Yeah, the group is this group is unimodular. It's actually unimodular. Yeah. Okay, so we have that, and then this is the one. Now, so look, I mean, here it's like the left-hand side of the Planck measure. We are integrating L2, integrating a function over the group. Okay. Now you want to write it in terms of L2, integrals with respect to some suitable measure over the unitary dual. In this case, we just have to focus on R star because this carries no measure of some analog of Fourier transform. Now, what is the Fourier transform? For each representation, this operator pi t. So let me write it now. Here I can erase. So pi t f over phi is equal to integral over h3 f of h. Okay, pi t of h dh. Now this is not very good, I'm afraid. Pi t of h over phi. We can stick an x here actually. So this, because we know what it is, what this guy is. This is phi of hx. There is an x here. Yeah, again, this is a linearization of pi t, right? It's a linearization of. Oh my God. Okay, so it's just that one. Now, this Hilbert-Schmidt, and this is Hilbert-Schmidt norm. You have to take Hilbert-Schmidt norm. This Hilbert-Schmidt norm, unfortunately, we don't see it in the abelian case at all because we just take square absolute value. But in this case, you have to go to Hilbert-Schmidt norm and square it, and then. So this is a remarkable formula now. So this is a very nice one. Okay, so I think now we have everything in place in order now to apply to the pre-trace formula in the case of H3 and get some conclusions about this. So I'm not going to do it now. I will do it on Wednesday before we move. So so next step is this now. Use the pre-trace formula. That's one application. To find out which components, which irreps of H3 here in its left regular representation on L2 of G mod gamma. You see, the left regular representation, there is no gamma. I mean, gamma is identity, it's just L2 of G. And in that case, for many, many groups, all irreps appear here, not in general. But in this case, this group is already co-compact, so you cannot expect that all irreps appear and all of them appear. Only some of them will appear, and to know which one is of interest. So this is one application of pre-trace formula. So this follows now. There's some technicality, but I mean, once we do that, then I will move to SL2R, and in that case, we can prove something which is exactly like the Poisson summation formula for SL2R, and maybe, hopefully, there will be time to prove this Selberg's Riemann hypothesis proof for I mean, prime number theorem and Riemann hypothesis for prime geodesics on hyperbolic Riemann surfaces. So I think that's good for now. Sorry, it took too much time actually, but anyhow. So any questions or?
Seems like a lot of work to decompose the left regular representations. Is it really that hard?
Yes, it's a lot of work. That's true. That's true. And guessing or obtaining the Plancherel measure is a lot of work that was done by Harish Chandra, at first Gelfand, Neymark, and then Harish Chandra. Yeah, it's indeed